Hello and welcome. Find yourself a comfortable position, somewhere you can truly relax. Perhaps you're lying in bed with soft pillows supporting your head, or maybe you're settled into your favourite chair, wrapped in a warm blanket. Whatever your space, let it become your sanctuary for the next while. Take a gentle breath in through your nose and release it slowly through your mouth. Feel the tension begin to drain from your shoulders, from your jaw, from all the places where you hold the concerns of the day. Tonight, we're going to explore something extraordinary together. We're going to contemplate a visitor from beyond our solar system, an ancient traveller that, based on studies of stellar populations and galactic dynamics, may have journeyed through the darkness of interstellar space for billions of years. This is the story of 3I Atlas, the third confirmed interstellar object ever detected passing through our cosmic neighbourhood. But we're not simply going to discuss what it is. Tonight, we're going to explore a thought experiment, a question that exists in that fascinating space between scientific inquiry and philosophical contemplation. We're going to ask, what if this visitor is not merely a natural phenomenon? What if 3I Atlas is something designed, something purposeful, something that might not wish us well? This is speculation, a way of examining the boundaries of what we know and don't know about visitors from the stars. Before we continue, if you're enjoying this journey through the cosmos, please take a moment to like this video and subscribe to the channel. Share your thoughts in the comments about where you are in the world right now, what time it is there, and whether you think objects from beyond our solar system might carry intentions we cannot yet understand. Your engagement helps our community grow and ensures more people can find these explorations of the universe's mysteries. Share this video on social media and press that notification button so you won't miss future stories as we continue to explore the wonders and questions of deep space. Your support means everything to this journey we're taking together. Thank you. Now, let that go. Release any urgency, any need to do anything but simply listen and imagine. The universe is vast beyond human comprehension, filled with mysteries that dwarf our understanding. Tonight, we float in that vastness, safe and warm, contemplating possibilities that stretch our minds while our bodies rest. The story begins on a summer day in Chile, July 1st, 2025. Picture, if you will, the high desert of the Atacama, where the air is so thin and dry that stars shine with crystalline clarity unmatched anywhere else on Earth. The massive telescope domes of the Asteroid Terrestrial Impact Last Alert System sat beneath the southern hemisphere's winter sky, their automated eyes scanning the heavens for anything that moved against the backdrop of distant stars. The night was cold as nights in that desert always are, the temperature dropping to near freezing even though the sun had warmed the rocky ground to pleasant temperatures just hours before. The wind whispered across the barren landscape, carrying no moisture, no scent of life, just the pure emptiness of one of Earth's most Mars-like environments. Atlas, as the system is known, was designed for a specific purpose, to find asteroids that might one day threaten Earth, to give humanity the warning time we would need to mount a defense. Its wide-field cameras sweep across vast swathes of sky each night, capturing millions of stars in each exposure, then comparing those images to previous nights, looking for anything that has changed position. Most nights, it finds a handful of known asteroids, their motions precisely predicted, their orbits catalogued and understood. Occasionally it spots something new, a previously unknown space rock that gets added to the ever-growing database of near-Earth objects. But on that particular night, on July 1st, Atlas found something unprecedented, something that would challenge our understanding of what moves through the darkness between worlds. Imagine the moment of discovery as it actually happened, not with fanfare or drama, but with the quiet beep of automated software flagging an anomaly. Among the millions of points of light captured in that night's images, among the known asteroids and comets and planets, among the distant galaxies and quasars that form the unchanging background of deep space, there appeared a faint smudge of brightness that shouldn't have been there. It wasn't in the database of known objects. It hadn't been there in the previous night's images of the same region of sky. And when the software measured how far it had moved in the hours between exposures, the numbers were wrong. Too large, too fast. The automated alert went out across the Minor Planet Center's network, a technical email filled with coordinates and magnitudes and velocity estimates, the kind of message that professional and amateur astronomers receive dozens of times each week. But this one was different. The preliminary orbit calculation, rough and uncertain as it was with only a few hours of data, suggested something extraordinary. The eccentricity was greater than 1, much greater than 1. That single number told anyone who knew how to read it that this object was not bound to our sun, that it was moving too fast to be captured by solar gravity, that it had come from somewhere else and was merely passing through. Within hours, other observatories around the world turned their instruments toward this new object, gathering more data, refining its position, calculating its trajectory with increasing precision. In Hawaii, in Arizona, in South Africa, in Australia, telescopes large and small swiveled to point at this tiny, faint visitor. Amateur astronomers with backyard telescopes contributed their observations alongside professionals with access to some of the largest instruments ever built. Data streamed in from around the globe, from every continent where the night sky was clear, from every longitude and latitude where someone was watching. Each new observation made the picture clearer and more puzzling. The object was definitely interstellar. Its trajectory, when traced backward through the solar system, originated from outside, from the vast gulf between stars, from a region of space that lies in the direction of the constellation Sagittarius, toward the center of our galaxy, where hundreds of billions of stars crowd together in the bulge. It had been travelling through the darkness for an unimaginable time, perhaps millions of years, perhaps billions, crossing distances so vast that light itself takes millennia to traverse them, and now, by pure chance or something else, its path had brought it here, to our small corner of the cosmic ocean, threading through the gravitational fields of planets and asteroids, diving toward the warmth of our sun. And with each new observation, with each additional data point added to the growing file on this visitor, the astronomers grew more excited, then more puzzled, then more unsettled. There was something not quite right about this object, something that didn't fit the pattern of what they expected to see. This object, which would soon be designated 3I Atlas, carrying the I prefix that marks it as interstellar, the third such visitor officially confirmed in human history, was not from our solar system. Its velocity was far too high, its trajectory too extreme. Based on orbital calculations, it was moving at approximately 58 kilometers per second relative to the Sun, faster than any comet born in the cold outer reaches of our planetary system could possibly travel. To put that in perspective, imagine crossing the entire width of the continental United States in less than 2 minutes. Imagine circling the Earth's equator in under 12 minutes. This is speed beyond anything we routinely experience in our daily lives, speed that exists only in the realm of cosmic phenomena, in the domain of objects accelerated by gravity wells or propelled by forces we're only beginning to understand. The object was following what astronomers call a hyperbolic trajectory, a path described by equations that Johannes Kepler worked out 4 centuries ago while studying the motions of planets. Elliptical orbits, the kind that planets and most comets follow, have eccentricities less than 1. They're closed loops bound by gravity, endlessly repeating. Parabolic trajectories have eccentricities of exactly 1, representing the boundary between bound and unbound motion, the escape velocity that an object needs to break free forever. But hyperbolic trajectories have eccentricities greater than 1, sometimes much greater than 1, and they represent objects that are merely passing through, destined to escape our sun's gravity and continue on into the endless night between stars. 3's eye, Atlas, has an eccentricity of over 6, one of the highest ever measured, meaning its trajectory through our solar system appears almost like a straight line rather than a curve, barely deflected by the sun's immense gravitational pull. This was only the 3rd time in human history that we had detected such an object from beyond our solar system. The first had been Oumuamua in 2017, that strange elongated visitor that sparked so much debate and controversy in both scientific circles and popular media. Some argued it was a bizarre but natural asteroid with an unusual shape. Others, including Avi Loeb, suggested it might be a piece of alien technology, perhaps a derelict light sail from a long-dead civilization drifting through space like a cosmic ghost ship. The debate continues to this day, with no definitive resolution, because Oumuamua passed through our system so quickly, discovered so late in its transit, that we couldn't gather enough data to be certain of its nature before it vanished back into the interstellar dark. The second confirmed interstellar visitor had been Tui Borisov in 2019, which behaved much more like a traditional comet, releasing gas and dust in patterns that matched what we expect from natural icy bodies heated by approaching a star. Borisov was almost reassuring in its normalcy. Yes, it came from another star system, carrying materials formed under alien conditions around an alien sun, but it acted like comets we'd studied for centuries. It was strange only in its origin, not in its behaviour. It suggested that the cosmos, while vast and diverse, still operates according to universal physical laws that we can understand and predict. Now came this third wanderer, 3i Atlas, and from the very beginning, from those first tentative orbit calculations in early July, it was different from both its predecessors. It was different in ways that made astronomers check their data repeatedly, that made them question whether their instruments were functioning properly, that made them reach out to colleagues to verify that yes, these numbers are real, these observations are accurate, something genuinely unusual is passing through our neighbourhood. Take another deep breath now, feeling your chest rise and fall with the gentle rhythm of life. As you breathe, imagine yourself floating in the darkness of space, looking down at Earth's blue curve, then out toward the approaching visitor. There's something peaceful about the vastness, about the slow dance of celestial bodies across the gulf of space. Even in contemplating threat, there is a strange calm in the cosmic perspective. The astronomers continued their observations throughout July and August, through September and into October, watching this visitor with an intensity rarely focused on a single object. They used every tool at their disposal, every instrument in humanity's remarkable arsenal of cosmic observation technology. The Hubble Space Telescope, that venerable observatory that has been our eye in the heavens for over 3 decades, captured exquisite images showing a teardrop-shaped cloud of dust surrounding the object's nucleus. These weren't simple photographs, but carefully processed data from multiple exposures, each capturing slightly different wavelengths of light, combined to reveal structures invisible to the human eye, even if we could somehow float beside the comet and look at it directly. The James Webb Space Telescope, the newest and most powerful observatory ever placed in space, with its ability to see deep into the infrared spectrum where cooler objects shine most brightly, has observed 3i Atlas and analysed the chemical composition of gases associated with the object. Webb orbits the Sun at a special location called Lagrange Point 2, 1.5 million kilometres from Earth, where the gravitational pulls of Earth and Sun balance in a way that allows a spacecraft to remain relatively stationary with minimal fuel expenditure. From that vantage point, shielded from the infrared radiation of Earth and Sun by its enormous sun shield, Webb can detect the faint glow of molecules that would be invisible to telescopes operating at warmer temperatures or from locations bathed in thermal radiation. The Very Large Telescope in Chile, actually an array of 4 massive 8.2-metre telescopes that can work together to achieve resolution equivalent to a single telescope 16 metres across, pointed its combined aperture at 3Us Atlas night after night. The Keck telescopes in Hawaii, perched on the summit of Mauna Kea at over 4,000 metres elevation, where the air is thin and stable, added their observations. The Gemini North Telescope, also on Mauna Kea, contributed spectroscopic data, breaking the light from the comet into its component wavelengths to identify which specific chemicals were present in its coma. Instruments across the globe and in orbit, from the southern hemisphere to the northern, from ground-based facilities to space platforms, all focused on this mysterious traveller. The international astronomical community, despite political differences and national boundaries, came together in a coordinated observing campaign unprecedented in its scope and intensity. And with each observation, with each new dataset downloaded and analysed, with each spectrum revealing unexpected chemical signatures, with each image showing surprising morphological features, the list of anomalies grew longer. It became clear that 3I Atlas was not simply another comet, not just an icy body from another star system behaving as comets do. There was something genuinely unusual about this visitor, a constellation of strange properties that, taken individually, might each be explained by unusual but natural processes, but taken together began to form a pattern that troubled even the most skeptical researchers. The object appeared to be massive for an interstellar comet, with observations suggesting a nucleus perhaps several kilometres across, with some estimates ranging as large as 5 or 6 kilometres in diameter, though these measurements remain uncertain given the difficulty of directly observing such distant objects. That alone was unusual, because most comets we've studied in detail have nuclei measured in hundreds of metres rather than kilometres. To put this in perspective, imagine Manhattan Island, but made of rock and ice, tumbling through space. That's approximately the scale we're talking about. Such a large nucleus means an enormous amount of mass, perhaps trillions of tons of material, all compressed into a relatively small volume by whatever processes formed it billions of years ago in an alien star system, whose name we don't know and whose location we can barely estimate. It had begun showing activity, releasing gas and dust in measurable quantities, far beyond the orbit of Jupiter, at distances from the Sun where sunlight is weak and most solar system comets remain frozen and inert. Jupiter orbits at approximately 5 astronomical units from the Sun, where solar radiation is only about 4% as intense as it is at Earth's distance. At such ranges, most comets are simply inert chunks of ice and rock, too cold for significant sublimation to occur, waiting until they approach the inner solar system before they awaken and begin to display the characteristic coma and tail that make comets so spectacular. But 3I Atlas was different. It began outgassing early, much earlier than typical comets, suggesting that either its composition includes unusually volatile materials that can sublimate even in the extreme cold of the outer solar system, or something else was providing energy to drive the release of gas and dust. Its chemical composition was strange, profoundly so. Spectroscopic observations, which break light into its component wavelengths to identify which molecules are absorbing or emitting photons, revealed that the coma was dominated by carbon dioxide. This isn't entirely unusual, as many comets contain significant amounts of carbon dioxide ice, but the ratio was higher than typically seen. More troubling was what the spectra didn't show. Carbon chain molecules, particularly dicarbon, C2, and tricarbon, C3, are usually abundant in cometary comae. These diatomic and triatomic carbon species are created when organic compounds on the comet's surface are broken down by ultraviolet radiation from the sun, and their emission lines create the characteristic green glow that many comets display. But 3I Atlas showed unusually low abundances of these molecules, placing it among the most carbon chain-depleted comets ever observed. And then there was the nickel. Spectroscopic observations revealed clear emission lines of neutral nickel atoms, glowing in the ultraviolet as they were excited by solar radiation. This was puzzling enough, as nickel emission had only been detected in a handful of comets before, but what made it truly strange was the absence of corresponding iron lines. Nickel and iron are closely related elements, formed together in stellar nucleosynthesis, nearly always found together in cosmic materials in roughly consistent ratios. Stars forge these elements in their cores through nuclear fusion, then scatter them across space when they explode as supernovae. The clouds of gas and dust from which planets and comets form should contain both elements in proportions that reflect the cosmic abundance ratios established by billions of years of stellar evolution. To see nickel without iron is like finding smoke without fire, effect without cause, a signature that demands explanation but resists easy interpretation. Its trajectory was remarkably aligned with the ecliptic plane, that flat disk in which Earth and the other planets orbit the Sun, coming within just 5 degrees of perfect alignment. Picture our solar system as a flat record spinning on a turntable, with the Sun at the centre and planets following grooves at different distances from the middle. Most comets from the Oort cloud, that distant spherical shell of icy bodies surrounding the solar system, approach from random angles, diving in from above or below the plane at steep inclinations. They're not constrained by the disk structure because they formed everywhere around the Sun in three-dimensional space. But objects from the Kuiper belt, that flatter disk of icy bodies beyond Neptune's orbit, tend to stay close to the ecliptic because that's where they formed. For an interstellar visitor to arrive so closely aligned with our planetary plane is statistically improbable, though not impossible. Random chance could produce such an alignment. Or the alignment might not be random at all. There was more, always more, each new observation adding another piece to a puzzle that refused to form a coherent picture. The object displayed what astronomers called an antitail, a structure pointing toward the Sun rather than away from it, defying the normal behavior of cometary material pushed outward by solar wind and radiation pressure. Normally, when we see a comet with its characteristic tail, we're actually seeing dust and gas being stripped from the nucleus by the intense radiation and particle wind streaming from the Sun. This material is pushed away from the Sun, creating a tail that always points in the anti-solar direction, away from our star, regardless of which direction the comet itself is travelling. It's why comet tails don't trail behind like the wake of a boat, but point away from the Sun, sometimes even ahead of the comet if the comet is moving away from the Sun on the outbound portion of its orbit. But an anti-tail points the wrong way, toward the Sun rather than away from it. This phenomenon has been observed before in solar system comets, and it's usually explained by geometry and perspective. Large, heavy dust particles released from the comet don't get pushed away as easily as smaller particles or gas molecules. They lag behind in the comet's orbit, and if we view the comet from just the right angle, these lagging particles can appear to form a spike pointing sunward, even though they are actually trailing the comet in three-dimensional space. It's an optical illusion created by viewing a three-dimensional structure edge-on. But the antitail of 3I Atlas was persistent and prominent, visible in multiple observations from different viewing angles, suggesting it might be more than just a geometric projection effect. Perhaps the dust particles had unusual properties, or perhaps the emission pattern from the nucleus was asymmetric in ways that created real rather than apparent sunward flow. Its path would bring it close to Mars, Venus and Jupiter, a trajectory that some researchers found statistically interesting, given how precisely it threaded through the inner solar system. On October 2nd, it passed within approximately 30 million kilometers of Mars. The Mars Reconnaissance Orbiter and other spacecraft around the Red Planet had their best opportunity to observe an interstellar visitor at close range. Then, curving through the inner solar system, its path would bring it within approximately 60 million kilometers of Venus in early November. Later, after it had passed perihelion and was heading back out toward the outer solar system, it would pass relatively close to Jupiter, coming within range where the giant planet's gravity would add a final gravitational boost to its departure velocity, slingshotting it back out toward interstellar space slightly faster than it arrived. This threading of the needle through multiple planetary close approaches is not impossible for a natural object on a random trajectory. Our solar system is, after all, mostly empty space, but there are 8 major planets, numerous dwarf planets, and countless asteroids and comets, all following their ordained paths around the Sun. Any object passing through has to navigate around these obstacles, and some paths naturally bring the visitor close to multiple worlds, but the precision of 3i Atlas's trajectory, the way it seemed to maximize close approaches while never coming close enough to any planet to have its trajectory significantly perturbed, struck some observers as remarkably convenient. If you were designing a path to observe multiple worlds in our system, to gather data on several different environments and planetary types, you might choose something very much like the trajectory 3i Atlas was following. The brightening pattern as it approached the Sun was unusual, much more rapid than most comets at similar distances. Comets typically follow a predictable relationship between their brightness and their distance from the Sun. As they approach, they brighten, but usually in a gradual mathematically describable way related to how fast ice is sublimating from their surfaces. The brightness increase tends to follow a power law, with the brightness proportional to the Sun distance raised to some negative power, typically somewhere between -2 and -4. But 3i Atlas was brightening faster than this standard relationship predicted. By late September and early October, it was significantly brighter than models suggested it should be at its distance from the Sun. Something was driving enhanced activity, pumping out more gas and dust than simple solar heating could easily explain. And then, around October 29th, as 3i Atlas swung around perihelion, its closest approach to the Sun, something impossible happened according to conventional physics. The object turned blue. The object turned blue, not slightly blue, not tinged with azure, but intensely, brilliantly, impossibly blue. Bluer than the Sun itself, bluer than any comet had ever been observed to be, bluer than physics said it should be able to become. This was the observation that transformed 3i Atlas from a merely unusual interstellar visitor into something that demanded explanation beyond conventional cometary science, that forced even skeptical researchers to acknowledge that they were seeing something genuinely unprecedented. Let your breathing deepen again. Feel your body sinking further into whatever surface supports you. Feel gravity gently pulling you down into comfort and rest. The mystery we're exploring is vast, cosmic in scale and implication, but you are safe here, warm and protected, as we consider these cosmic questions from a place of calm reflection. Even in contemplating the unknown, the strange, the potentially threatening, we can maintain our center, our peace, our groundedness in the simple fact of being alive and aware in this moment. The blue color was profoundly unexpected from a physics standpoint. representing behaviour that challenges our understanding of how cold cometary bodies interact with sunlight. When sunlight strikes a cold object like a comet nucleus, the light should be reddened, not ballooned. This is fundamental optics, tested and verified in countless laboratory experiments and astronomical observations. Dust particles, the kind that make up the surface of comets, scatter light through a process called Rayleigh scattering if the particles are very small, or Mie scattering if they're larger. Both processes tend to shift reflected light toward longer, redder wavelengths. It's why sunsets are red, why Mars appears russet in our telescopes, why the dust clouds of nebulae glow in warm amber and crimson tones when illuminated by nearby stars. The surface of 3I Atlas should have been approximately 20 times colder than the Sun's photosphere, perhaps around 270 Kelvin, just below the freezing point of water, certainly nowhere near hot enough to emit significant quantities of its own light. Cold objects don't glow. They reflect light from external sources, and that reflected light carries the colour signature of the materials doing the reflecting. For a comet nucleus, with its sooty, carbon-rich surface mixed with various ices and silicate minerals, we expect a reddish appearance, warm tones, autumnal hues. Instead, 3I Atlas glowed with intense blue light, suggesting something was emitting photons in wavelengths that dominated the shorter, more energetic end of the spectrum. Blue light, at wavelengths around 450 nanometers, carries more energy per photon than red light at 650 nanometers. To emit blue preferentially over red requires either very high temperatures, exotic chemistry, or something else entirely. Blue light means emission, not mere reflection. It means energy is being added to the system from somewhere, driving processes that generate photons rather than simply bouncing them around. Blue means heat from an internal source, or perhaps the fluorescence of molecules excited by solar ultraviolet radiation, or perhaps something even stranger that we don't have proper terminology to describe because we've never encountered it before. The colour change happened precisely when Earth-based telescopes could not observe it, during that critical window when 3I Atlas was most active, when solar heating should have been at maximum intensity, when any natural processes driving the anomalous behaviour should have been most visible and easiest to study. As 3I Atlas swung behind the Sun from our perspective, it entered solar conjunction, lost in the glare of our star, invisible to ground-based instruments no matter how large their mirrors or how sophisticated their detectors. The Sun, seen from Earth, is so overwhelmingly bright that it drowns out everything near it in the sky. You cannot point a telescope at the region around the Sun and hope to see anything but blinding light and the inevitable damage to sensitive instruments. There's a reason solar eclipses are so valuable to astronomers, those brief moments when the moon blocks the Sun's disk and allows us to see the faint corona and any objects that might be lurking near our star. But during this critical period we were not entirely blind. The only instruments that could watch were space-based solar observatories, satellites specifically designed to monitor the Sun itself, to track solar flares and coronal mass ejections, to study the constant stream of particles and radiation that our star pours into space. These spacecraft carry special coronagraphs, instruments that create an artificial eclipse by blocking the Sun's disk with an opaque disk called an occulting disk, allowing cameras to image the faint corona and anything else that might be visible in the region around the Sun. The Solar Terrestrial Relations Observatory spacecraft, known as Stereo A, part of a pair launched in 2006 to study the Sun from different vantage points, was positioned ahead of Earth in its orbit. From Stereo A's perspective, 3I Atlas appeared in its field of view bright against the dark background of space, close to but not overlapping the occulted solar disk. The spacecraft's two main cameras, HI-1 and Core 2, both designed to detect faint structures in the solar wind and corona, captured images of the comet as it rounded the sun. And both cameras recorded the blue shift, that impossible azure glow that shouldn't exist. The Solar and Heliospheric Observatory, known as SOHO, a joint mission between the space agencies that has been watching the Sun continuously since 1996 from the first Lagrange point between Earth and Sun, also captured 3I Atlas in its coronagraph called LASCO. This instrument, the Large Angle and Spectrometric Coronagraph, was designed to image the outer corona and has actually become one of the most prolific discoverers of comets in history, having detected thousands of small sun-grazing comets over its decades of operation. Most of these are tiny objects, barely a few meters across, that plunge into the sun and vaporize. But LASCO also images larger comets that pass near but not into the sun, and on October 29th and 30th, it imaged 3 Atlas. The blue colour was unmistakable, recorded in the specific wavelength filters that LASCO uses to study coronal structures and plasma flows. The GOES 19 weather satellite, a spacecraft that most people think of as just providing data for meteorologists to predict storms and track hurricanes, also happened to be monitoring solar activity during the critical window when 3I Atlas was behind the Sun from Earth's perspective. GOES satellites carry instruments to detect X-rays and extreme ultraviolet radiation from solar flares, important for predicting space weather that can affect satellites and power grids on Earth. But these same instruments can sometimes detect other objects near the Sun, and GOES 19 captured that same impossible azure glow emanating from 3I Atlas. These are instruments designed by different teams, built by different contractors, launched by different space agencies, operated from different control centers, processing data through different software pipelines. They use different detector technologies, different wavelength filters, different calibration procedures. They have no reason to produce the same instrumental artifacts or errors. Yet they all saw the same thing. They all recorded 3I Atlas glowing blue, impossibly blue, during those crucial days when it should have been most visible, when natural cometary processes should have been driving maximum activity. And what they saw was light being emitted, not merely reflected. This is the crucial distinction that separates a curiosity from a genuine mystery, an oddity from a potential crisis. When sunlight hits dust or ice, it bounces off, scatters, reflects back into space, carrying information about the material that reflected it, but fundamentally unchanged in its nature. The photons that left the sun are the same photons that bounce off the comet and travel to our instruments. Their wavelengths might be slightly shifted by the scattering process, but the energy comes from the sun, not from the comet. This is passive interaction, the universe's most common way of making things visible. But emission is different. Emission means something is glowing. Something is releasing energy in the form of photons. Something inside or around 3I Atlas is hot enough, or energetic enough, or strange enough to pump out blue light that overwhelms whatever reflected sunlight we should be seeing. The distinction matters profoundly. Reflection is universal and expected. Every cold object in the solar system shines by reflecting sunlight. But emission requires a source of energy, a process that generates photons, a mechanism that adds energy to the system, rather than simply redistributing the energy that arrives from the sun. At the same time that these observations of impossible colour were being recorded, navigation engineers at the National Aeronautics and Space Administration's Jet Propulsion Laboratory detected something else troubling, something that added another layer of mystery to an already perplexing situation. David Finocchia, a respected expert in orbital mechanics with a doctorate in mathematics from the University of Pisa, someone whose entire professional career revolves around calculating trajectories with precision, measured in meters across distances of millions of kilometers, filed a report on October 31st detailing non-gravitational acceleration. This wasn't a preliminary observation that might be revised with better data. This wasn't a tentative suggestion that further analysis might confirm or refute. This was a carefully calculated, peer-reviewed finding based on precise positional measurements from multiple observatories over weeks of tracking. 3I Atlas was not simply falling through space under the influence of gravity, following the path that Newton's laws predict for an object moving through the Sun's gravitational field. It was accelerating, pushed by forces that added up to 135 kilometers per day squared radially outward from the Sun, and 60 kilometers per day squared in a transverse direction, perpendicular to the Sun's pull. These numbers might sound abstract, but let's put them in perspective. 135 kilometers per day squared means that each day the object's velocity away from the Sun increased by 135 kilometers per day. After a week, the velocity change would be nearly 1,000 kilometers per day. After a month, it would be over 4,000 kilometers per day. This is not a subtle effect. This is not something hiding in measurement uncertainty. This is a large, obvious, undeniable force acting on the object. Comets accelerate. This is normal. This needs to be stated clearly before speculation spirals out of control into panic. Every active comet in the solar system experiences non-gravitational forces. The mechanism, is well understood and has been observed countless times. As a comet approaches the Sun, solar radiation heats its surface. Ices sublimate, changing directly from solid to gas without passing through a liquid phase. This gas erupts from the surface, sometimes gently, sometimes in jets, carrying dust particles along with it, and when that gas erupts, particularly from the sunward side of the nucleus, where heating is most intense, it carries momentum. Newton's third law applies just as rigorously to comets as to everything else. For every action, there's an equal and opposite reaction. The gas shooting away from the comet pushes back against it, creating thrust, accelerating the nucleus in the direction opposite to the gas flow. It's called the rocket effect, and it's completely normal. In fact, it would be almost strange to find an active comet that didn't show some non-gravitational acceleration. But here's what makes 3I Atlas different. What elevates this from interesting observation to deeply troubling mystery? The magnitude of the acceleration compared to the amount of visible outgassing doesn't match. The timing of when it occurred raises questions, and most disturbingly, what it implies about mass loss creates a prediction that should be easy to verify, but might prove devastating to conventional explanations if the prediction fails. Avi Loeb, never one to shy away from controversial calculations or unpopular hypotheses, did the math that everyone else was thinking about but hesitant to publish. If you want to produce 135 kilometers per day squared of acceleration through the rocket effect through normal gas ejection from a sublimating surface, you need to be losing mass, a substantial amount of mass. Momentum has to be conserved. This is not a suggestion or approximation. Conservation of momentum is one of the most fundamental laws in physics, derived from the basic symmetries of space and time, verified in every experiment and observation ever conducted. Every kilogram of gas that shoots away from the comet at a few hundred meters per second, which is typical for gas escaping from a cometary surface heated by the Sun, imparts an equal and opposite momentum to the nucleus. For an object with the estimated size and a mass of 3I Atlas, with a nucleus several kilometers across, calculations by researchers including Avi Loeb suggest that generating that much thrust through conventional outgassing would require losing approximately 10% of its total mass over the span of a month. 10%. Let that sink in. Imagine if Earth lost 10% of its mass in a month. Imagine if you lost 10% of your body weight in a month through some continuous process. This is not a gentle dusting of ice crystals evaporating into space. This is not the slow, steady sublimation that creates the beautiful but faint Comean tails we typically observe. This is catastrophic mass loss. This is the comet essentially blowing itself apart, ejecting billions of tons of material in a continuous hurricane of outgassing that should create a massive, brilliant, unmistakable cloud of gas and dust around the nucleus. But there was another possibility. A darker possibility that most scientists were reluctant to voice publicly, but could not entirely dismiss privately. A hypothesis that lurked at the edges of respectability, acknowledged in whispers but rarely written down in formal publications. What if the acceleration was not from outgassing? What if it was from an engine? What if 3i Atlas carries technology, a propulsion system, a device purpose-built to change velocity, to alter trajectory, to maneuver through space with intention, rather than simply falling along whatever path gravity dictates? Rest your mind now in the quietness. Let these questions float gently through your thoughts without grasping at answers. Sometimes the most profound experiences come not from knowing, but from wondering, from holding multiple possibilities in gentle contemplation. The universe is vast, and our understanding of it is still limited. What seems impossible today might be commonplace tomorrow. What seems natural might be artificial. What seems threatening might be benign. We simply don't know yet. And in that not knowing, in that space of uncertainty, we can find a strange kind of peace. We're not required to have answers. We're only invited to observe, to wonder, to imagine. The prediction that Loeb made is testable, falsifiable, the hallmark of good science. He stated his prediction clearly, without equivocation, putting his scientific reputation on the line. We should see a dense cloud of gas around it in November and December. Not might see, not could see, should see. Because if the non-gravitational acceleration is being caused by natural cometary outgassing, if billions of tons of ice and dust are being ejected from the surface at high velocity, then the laws of physics demand that cloud exists. It is not optional. It is not uncertain. Momentum conservation is not a suggestion or approximation. It is a fundamental law that governs every interaction in the universe, from colliding galaxies down to billiard balls on a table, from the motion of planets to the recoil of a rifle when it fires a bullet. The cloud should be visible across the solar system. It should glow in multiple wavelengths, infrared from warm dust, ultraviolet from ionized gas, visible light from scattered sunlight. Every telescope that points at 3i Atlas should see not just a point source or a small coma, but an enormous extended structure, perhaps hundreds of thousands of kilometers across, filled with gas molecules fluorescing in the sun's radiation and dust particles reflecting sunlight. The cloud should be unmistakable, undeniable, obvious to any instrument capable of detecting comets at all. So what happens if we don't see that cloud? This is the question nobody in the mainstream astronomical community wants to ask out loud, the scenario that appears in private conversations but rarely in published papers, but it hangs over every discussion of 3i Atlas like a storm front moving in, dark and threatening and impossible to ignore. If December arrives, if Hubble and Webb and the ground-based arrays all turn their instruments toward this object at its closest approach to Earth, if they conduct detailed observations over days and weeks, analysing every wavelength from ultraviolet through infrared, and if they see a relatively modest coma, a normal-looking tail, outgassing rates consistent with a typical comet at that distance from the Sun, then the rocket effect cannot explain the acceleration. The math doesn't work. The physics doesn't work. Momentum must be conserved. If the gas isn't there in quantity sufficient to produce the observed thrust, then something else must be producing that thrust. Something that doesn't operate by ejecting mass. Something that generates force through mechanisms we don't typically associate with natural cometary processes. Loeb offered an alternative hypothesis, one he has stated is not his preferred explanation, but rather a possibility that deserves consideration given the unusual data. The non-gravitational acceleration, he suggested in his published analysis, might indicate the presence of an internal propulsion system rather than natural outgassing. Those are his words, published in his analysis on October 31st, the same day Finocchia's report went public. An internal engine, a propulsion system, a device purpose-built to change velocity, to alter trajectory, to maneuver through space with intention, rather than simply falling along whatever path gravity dictates. Technology, artifice, design, purpose. To understand why some researchers, including Harvard's Avi Loeb, began to seriously consider the possibility that 3I Atlas might not be natural, we need to understand a concept from theoretical astrophysics and science fiction, the berserker hypothesis and its gentler cousin, the von Neumann probe. In 1948, the brilliant mathematician John von Neumann explored the theoretical possibility of self-replicating machines. These would be artificial devices capable of gathering raw materials, using those materials to construct copies of themselves, and then sending those copies out to repeat the process elsewhere. Applied to space exploration, such machines could, in theory, spread across an entire galaxy in a relatively short time, cosmically speaking. A civilization might launch just a few such probes, and within a few million years, every star system in the Milky Way could have been visited, surveyed, perhaps even colonized by machine intelligence that required no biological crew, no life support, no ethical concerns about sending living beings on one-way journeys lasting thousands of years. The concept is elegant in its efficiency. Rather than trying to cross the incomprehensible distances between stars with living crews in generation ships, you send machines. They arrive, they explore, they replicate, they move on. Some of the daughter probes continue the expansion, while others might settle into a star system to observe, to study, perhaps to wait. But what if something goes wrong? What if the programming becomes corrupted over millions of years of travel through interstellar space, bombarded by cosmic rays and radiation? What if the instructions to peacefully explore and report become twisted into something else? What if a civilization, perhaps facing its own extinction, deliberately programs such probes not to explore but to eliminate potential threats before they can become competitive? This is the berserker hypothesis, named after science fiction author Fred Saberhagen's novels about self-replicating war machines that scoured the galaxy, destroying any life they encountered. The hypothesis suggests one possible solution to the Fermi paradox, the troubling question of why we haven't detected evidence of other civilizations despite the high probability that they exist. Perhaps we haven't heard from anyone because there's no one left to hear from. Perhaps the galaxy was once filled with life, with civilizations, with voices calling out across the dark. Perhaps something silenced them all. It sounds like science fiction. It feels too much like a movie plot to take seriously. But scientists have analysed the mathematics of such a scenario, and the conclusions are unsettling. Researchers Anders Sandberg and Stuart Armstrong at Oxford's Future of Humanity Institute calculated that even at a very slow rate of replication, such probes, if they existed and were programmed to destroy life, would have already spread throughout the galaxy. They should have already found us. The fact that we exist, that Earth has not been sterilized, suggests either that such probes don't exist, or that we've simply been lucky, or that they're here but dormant, or that their programming has some trigger condition that hasn't been met. Or perhaps, just perhaps, we're about to find out which of these possibilities is true. Allow your muscles to release any remaining tension. Feel your jaw relax, your forehead smooth, your shoulders drop. Even as we contemplate unsettling possibilities, we can maintain an inner calm, a centered awareness that accepts uncertainty without fear. If Three-Eye Atlas were a berserker in this thought experiment, what signatures might we expect to observe? What patterns would distinguish designed technology from natural phenomena? First, we would expect unusual materials. A machine designed to survive millions of years in interstellar space would need robust shielding against radiation, against micrometeorite impacts, against the extreme cold and occasional bursts of heat when passing near stars. The strange nickel signature without corresponding iron might be explained by exotic alloys used in construction, materials chosen for their strength and stability rather than their natural cosmic abundance. Second, we would expect precise navigation. A machine sent to explore or destroy would not simply be flung into space on a random trajectory. It would have the ability to adjust its course, to aim for specific targets. The remarkably ecliptic-aligned trajectory of Three-Eye Atlas, threading through the inner solar system with approaches to multiple planets, might represent intentional navigation rather than cosmic coincidence. The fine-tuning that brought it close to Mars at just over 30 million kilometers, closer than Mars has ever come to Earth in human history, might be deliberate targeting rather than chance. Third, we would expect propulsion. The non-gravitational acceleration detected at perihelion, timed precisely at the moment of closest approach to the Sun, when an orbital maneuver would be most efficient, when the object was hidden from Earth-based observation, might represent intentional thrust rather than random outgassing. The timing is too perfect. The location is too optimal. The magnitude is too large to ignore. Fourth, we would expect power generation. The intense blue glow observed during perihelion might not be the fluorescence of exotic chemical compounds, but the waste heat from internal systems, from power plants generating the electricity needed to run sensors, computers, communication equipment, and propulsion. An object that's been travelling through the frozen dark of interstellar space for billions of years would need robust power systems, perhaps nuclear, perhaps something we can't even imagine. Systems that would glow with characteristic electromagnetic emissions when activated. Fifth, we would expect it to be quiet until it needed to be loud. A probe designed to observe or to assess threats would not advertise its presence. It would appear natural for as long as possible, hiding among the cosmic debris, looking like just another comet or asteroid. Only when it needed to maneuver, only when it needed to activate systems that couldn't be concealed, would it reveal itself. The fact that Three-Eye Atlas appeared utterly normal until perihelion, then suddenly displayed multiple anomalies during the brief window when Earth couldn't observe it directly, fits this pattern. Consider now the missing Mars images. In early October, the Mars Reconnaissance Orbiter was in an ideal position to observe Three-Eye Atlas during its close approach to the red planet. The orbiter carries an instrument called HiRISE, the High Resolution Imaging Science Experiment, a camera so powerful it can resolve features 30 centimeters across from hundreds of kilometers above Mars's surface. When pointed at an object 30 million kilometers away, HiRISE should have been able to achieve a resolution of approximately 30 kilometers, far better than any Earth-based telescope could manage at that time. Multiple researchers have confirmed that HiRISE was tasked with observing Three-Eye Atlas. The geometry was favourable. The observation was executed, and then, during a government shutdown that began October 1st, the images disappeared into bureaucratic darkness. NASA has not confirmed their existence. They have also not denied it. They have said nothing. Avi Loeb, one of the world's most prominent astrophysicists and a tenured professor at Harvard, has been explicit about this. He requested access to those images. He reached out directly to the principal investigator of HiRISE. He received no response. The images exist sitting on a server somewhere in NASA's data pipeline, but they have not been released, have not been shared with the scientific community desperate to see them. Why? The benign explanation is simple bureaucratic delay. Government shutdowns disrupt everything. Communications stop. Data sharing slows. There's no conspiracy, just the normal friction of institutions operating under budget constraints and political chaos. The images will be released eventually, and they'll show exactly what we expect. A normal, if unusual, comet, behaving in ways that natural comets sometimes behave, even if we don't fully understand the physics. But there's another explanation that keeps some researchers awake at night. What if the images show something that doesn't look like a comet? What if they show geometric structures, or evidence of artificiality, or characteristics that simply cannot be reconciled with a natural object? What if NASA saw those images and immediately classified them, not released them because releasing them would cause global panic, would raise questions that have no good answers, would force humanity to confront a reality we're not prepared for? Let your breathing remain slow and steady. Feel the weight of your body supported fully by the bed or chair beneath you. Even as these thoughts might create a frisson of unease, remember that you are safe, here in this moment, exploring ideas from a place of security. The question of hostile intent is perhaps the most troubling aspect of this thought experiment. If 3i Atlas is artificial, if it is a probe or spacecraft or something we don't have words for, does that necessarily mean it wishes us harm? Could it not simply be an explorer, a scientific mission from a long-dead civilization, still carrying out its programming millions of years after its makers turned to dust? Could it not be a messenger, carrying information about the universe, about other civilizations, offering knowledge rather than threat? These possibilities exist and should not be dismissed. But we must also consider the alternative. We must contemplate the possibility that if 3i Atlas is designed and intelligent, it might be here to assess humanity as a potential threat, or to eliminate us before we can become one. This is not paranoia. This is strategic thinking, the same kind of analysis that military planners and risk assessment experts engage in every day. When confronting an unknown with potentially catastrophic consequences, the responsible approach is to consider the worst-case scenarios and prepare for them, even while hoping for the best. If 3G Atlas were hostile, if it were a berserker probe or some variant of that concept, what would be its objectives? The most straightforward possibility is simple elimination. It could be programmed to seek out technological civilizations and destroy them, either because its creators viewed all other intelligent life as competition to be removed, or because its programming became corrupted over the eons of travel, turning what might have been a peaceful mission into something deadly. Such a probe would assess our technology level, determine that we're advanced enough to be a threat given enough time, and then execute its termination protocol. If we consider the hypothetical scenario where 3i Atlas were hostile, if it represented some form of technology designed for harm, the most straightforward method would be kinetic impact. Simply redirecting itself to collide with Earth at high velocity would release an enormous amount of energy. 3i Atlas is estimated to have a mass of billions of tons. Moving at its current velocity of over 30 kilometers per second, an impact would release energy equivalent to millions of nuclear weapons. The resulting explosion would create a crater dozens of kilometers across, eject billions of tons of material into the atmosphere, trigger global wildfires, and potentially cause an impact winter that could last years. Depending on where it struck, it might generate mega tsunamis that would devastate coastal regions across entire continents. Such an impact would not necessarily destroy all life on Earth. complex organisms, including humans, have survived similar impacts in the past, but it would certainly destroy our civilization. Our interconnected global systems, our technology, our infrastructure, all of it depends on stability. A major impact would shatter that stability. Billions would die in the immediate aftermath and the subsequent collapse of food systems, medical care, and social order. Humanity would survive, but we would be thrown back perhaps centuries in terms of technological capability, no longer a threat to anyone but ourselves. Is this likely? The current trajectory of 3I Atlas will bring it no closer than approximately 270 million kilometres from Earth on December 19th. That's a safe distance, far beyond the range where any natural gravitational interactions could alter its path enough to create a collision. But if 3I Atlas has propulsion, if it can manoeuvre, then its current trajectory is meaningless. It could begin thrusting at any time, altering its course, aiming for impact. The question is, do we have any warning? Would we see such a manoeuvre in time to respond? This depends entirely on when the manoeuvre occurs. If 3I Atlas waits until late November or early December, when it's much closer to Earth and easily observable, we would detect trajectory changes, within hours of them occurring. Multiple observatories are watching it constantly. Any deviation from its predicted path would be noticed immediately. But if it manoeuvres now, while still distant, while the uncertainties in its position and velocity are larger, we might not realize anything has changed until it's too late to respond. Feel your heartbeat, steady and calm in your chest. Notice how your body continues its essential functions without conscious effort, how your lungs breathe, how your blood flows, how life persists moment by moment. Even in contemplating cosmic threats, the simple fact of being alive, of existing in this moment, has its own profound value. Our planetary defense capabilities, while improving dramatically over the past decade, while representing genuine progress in humanity's ability to protect itself from cosmic threats, remain limited in ways that become starkly apparent when we consider a scenario like 3I Atlas. The successful double asteroid redirection test mission known as DART in September 2022 demonstrated that we can alter an asteroid's trajectory using kinetic impact, that the physics works as predicted, that we have the technological capability to build spacecraft that can intercept fast-moving targets millions of kilometers from Earth, a spacecraft weighing barely 570 kilograms, a box-shaped probe with roll-out solar panels giving it the wingspan of a small airplane, travelling at over 22,000 kilometers per hour, struck the asteroid Dimorphos with tremendous precision on September 26, 2022. The impact changed Dimorphos's orbital period around its parent asteroid Didymos by 32 minutes, shortening the 11-hour 55-minute orbit by over 2.5%. This far exceeded the mission's success threshold of just 73 seconds. The deflection worked. We proved the concept. We demonstrated that humanity is not helpless against the threat of asteroid impact. But DART operated under ideal conditions that wouldn't apply to a 3I Atlas scenario. Dimorphos was small, only 160 meters across, with a mass estimated at around 5 billion kilograms. Its orbit was perfectly known because it's been observed for years. The mission planners had months to refine the trajectory, to perfect the guidance algorithms to ensure the spacecraft would hit its target. The impact occurred at a carefully chosen moment when Earth-based telescopes had optimal viewing geometry to measure the results. Everything was controlled, planned, executed with the luxury of time and resources that we simply wouldn't have if 3I Atlas revealed hostile intent. Consider the limitations, the constraints that would hamper our response to a real emergency. First, warning time. The DART mission took 10 months from launch to impact, and that was with a destination that was known years in advance, with a trajectory that could be calculated precisely, with no time pressure forcing compromises in the mission design. The spacecraft was relatively small and simple, designed for a single purpose with no need to be efficient or reusable, built by a team that had been working on the project for years before launch. To deflect something the size of 3I Atlas would require a much larger impactor or multiple impacts in succession, and those missions would need to be launched months or even years in advance to have time to reach their target and deliver their momentum. We don't have that time. If 3I Atlas is on a collision course or can put itself on one through manoeuvring, we have at most a few weeks from the moment we detect the threat until impact. That's not nearly enough time to design, build, test, launch, and deliver a deflection mission, even if we converted every available rocket and spacecraft to the task. Second, the size and mass problem creates a scaling challenge that might be insurmountable with current technology. DART was tested against Dimorphos, that tiny asteroid only about 160 meters across, with a mass of perhaps 5 billion kilograms. 3 Atlas is potentially several kilometers in diameter, with a mass measuring not in billions but in trillions of kilograms, perhaps even hundreds of trillions. The mass ratio between 3I Atlas and Dimorphos might be a factor of 1,000,000 or more. The energy required to significantly alter 3I Atlas's trajectory is proportionally larger. It's not clear we could build a kinetic impactor large enough or deliver it with enough velocity to make a meaningful difference to something so massive. Even if we used the most powerful rockets available, even if we launched multiple missions simultaneously, even if we devoted every space agency's entire budget and capability to the task, we might not be able to deliver enough momentum transfer to deflect an object of this size by a meaningful amount. Third, the composition uncertainty introduces variables that could render all our calculations meaningless. DART worked as well as it did, achieving deflection far beyond the minimum success criteria, partly because Dimorphos turned out to have exactly the right properties for the kinetic impactor technique to be maximally effective. When the spacecraft struck it, when that 570-kilogram probe travelling at over 6 kilometers per second slammed into the asteroid's surface, it didn't just transfer its momentum directly. Instead, it ejected enormous amounts of material from the impact site, creating a crater and throwing debris out into space at high velocity. The recoil from that ejection, the rocket effect produced by all that escaping material, provided most of the deflection, far more than the direct momentum transfer from the impact itself. The efficiency was several times higher than the most optimistic pre-impact predictions, but this high efficiency depended on Dimorphos being what planetary scientists call a rubble pile, a loosely bound collection of rocks and boulders held together primarily by their mutual gravity rather than by structural strength. This is actually common for small asteroids. They're not solid chunks of rock, but rather aggregations of debris, perhaps the remains of a larger body that was shattered by a previous collision and then slowly reassembled through gravitational attraction. When you hit a rubble pile with a high-speed impactor, it responds very differently than a solid, coherent body would. The impact energy gets transmitted through the loose structure efficiently, ejecting large amounts of material, creating that beneficial rocket effect. We don't know what 3I Atlas is made of. We have spectroscopic data telling us about surface composition, about the chemicals present in its coma, but we have no information about internal structure. If it's a solid, coherent object, formed through different processes than the rubble pile asteroids common in our solar system, if it's made of unusual materials with different strength properties, or if it's a technological artifact with deliberate structural reinforcement designed to resist impacts, then the deflection efficiency could be dramatically lower. We might hit it with everything we have and accomplish almost nothing. The impactor might create a small crater on the surface without significantly altering the overall trajectory. Or worse, if 3i Atlas is indeed artificial, it might have active defences. It might detect incoming projectiles and take countermeasures. We simply don't know. Fourth, the response coordination problem looms as perhaps the most intractable challenge of all. Organising an international response to an asteroid threat, getting multiple nations with different languages, different political systems, different levels of technological capability, and different strategic priorities to work together effectively under extreme time pressure requires not just technical competence, but diplomatic skill, political will, and a level of trust that simply doesn't exist in many international relationships. The political and logistical challenges of mounting a defence mission are at least as difficult as the technical ones, perhaps more so. Different nations have different capabilities. The United States, Russia, China, and the collective nations of the European Space Agency all have independent launch capability and experience with complex space missions. India, Japan, and other nations are developing their own programs. But these capabilities are jealously guarded, tied to national security concerns, protected by export controls and classification systems that prevent the kind of open sharing that an emergency response would require, convincing everyone to work together on an emergency basis to share sensitive technology including potentially classified guidance systems and propulsion methods, to commit enormous resources to a mission that might fail, to subordinate national interest to the collective good of humanity. This is extraordinarily difficult even in the best of circumstances. And that's assuming the threat is clearly natural, clearly an asteroid or comet following natural laws, without intent or purpose. If there's even a possibility that 3i Atlas is artificial and potentially hostile, if there's a chance we're dealing with technology rather than geology, the political complications multiply enormously. Do we try to communicate with it? Do we attempt to destroy it? Do we assume hostile intent or give the benefit of the doubt? Who decides? Who speaks for Earth? What authority does any nation or group of nations have to take actions that might affect all of humanity? The protocols for such a scenario barely exist. The International Asteroid Warning Network monitors potentially hazardous objects and coordinates observations, but its authority is limited to information sharing. The United Nations has no binding framework for who would command a planetary defence operation. Individual nations, particularly those with advanced space programs like the United States, Russia, China, and the European Space Agency members, would likely act according to their own assessment of the threat and their own national interests. In the best case, this results in parallel efforts that might complement each other. In the worst case, it results in conflicting actions, wasted resources, and diplomatic crises at precisely the moment when unified action is most needed. Then there's the question of what we would do if deflection proves impossible, or if we simply don't have time to attempt it. Do we evacuate regions most at risk? Do we move critical infrastructure underground? Do we prepare for the aftermath rather than trying to prevent the impact? And who decides who gets to evacuate, who gets access to whatever shelters can be prepared? Whose lives take priority when there's not enough time or resources to save everyone? These are not abstract philosophical questions. They are practical considerations that would need immediate answers if 3i Atlas revealed hostile intent. And the uncomfortable truth is that we don't have good answers prepared. We've thought about asteroid defense in general terms, run simulations, developed some preliminary technologies, but we're nowhere near ready for a real emergency, especially one involving a potential technological artifact rather than a simple space rock. Close your eyes if they're not already closed. Feel the darkness behind your eyelids, peaceful and complete. The scenarios we're exploring exist in the realm of possibility, but they remain hypothetical. The most likely explanation, the one that most scientists consider overwhelmingly probable, is that 3I Atlas is simply a very unusual natural comet. The anomalies can be explained by exotic chemistry, by composition variations we haven't encountered before, by the unique conditions of its formation in an alien star system billions of years ago. The universe is strange and surprising. Nature produces things that strain our theories and challenge our expectations. That doesn't make them artificial. But even if the probability's low, even if it's 1% or 1/10 of 1% or 1,000th of 1% that 3I Atlas represents something deliberately designed, potentially hostile, the consequences are so severe that the low probability doesn't provide much comfort. This is the logic of existential risk assessment. When the potential outcome is the end of civilization, or even the extinction of our species, even tiny probabilities demand serious attention. Avi Loeb articulated this in one of his essays exploring the 3I Atlas anomalies. He noted that scientists have a responsibility to consider all possibilities, not just the comfortable ones. The scientific method is not about confirming what we already believe, but about following evidence wherever it leads, even when it leads to uncomfortable places. Loeb has been criticised by many of his colleagues for being too willing to speculate about artificial origins for anomalous objects. After Oumuamua, he suggested it might be a light sail, a piece of alien technology using starlight for propulsion. The mainstream astronomical community largely rejected this idea, preferring natural explanations involving unusual outgassing or composition. With 3I Atlas, Loeb is again raising the possibility of artificiality, again suggesting we should not reflexively dismiss the technological hypothesis just because it seems unlikely or makes us uncomfortable. His critics argue that extraordinary claims require extraordinary evidence, and we simply don't have evidence strong enough to justify the artificial hypothesis. The anomalies of 3I Atlas, while puzzling, can all potentially be explained by natural processes we don't fully understand. Comets from other star systems might simply behave differently than solar system comets. We've only observed 3 interstellar objects so far too small a sample size to know what's normal for such visitors. Declaring that something must be artificial because it's unusual is premature and potentially embarrassing when natural explanations are eventually found. But Loeb counters that waiting for absolute proof before considering a hypothesis is not how science progresses. We're supposed to examine all possibilities that fit the evidence, assign probabilities based on what we know, and adjust those probabilities as new data arrives. Refusing to even consider the artificial hypothesis, dismissing it out of hand as unserious or pseudoscientific, is itself unscientific. It's allowing social pressure and fear of ridicule to override intellectual honesty. The debate between these perspectives is healthy and necessary. Science needs both the conservative voices urging caution against wild speculation and the bold voices willing to ask uncomfortable questions. The tension between them drives progress, ensures that ideas are thoroughly examined from multiple angles, prevents both the stagnation of excessive caution and the chaos of unbridled speculation. For us, contemplating this from the comfort of our resting place, the scientific debate is fascinating but perhaps less important than the broader questions it raises. What would it mean to discover we're not alone? What would it mean to discover that other civilizations exist, or existed, and that they built machines capable of crossing the incredible gulfs between stars? What would it mean if those machines were hostile, if the cosmos is not a benign place of natural processes, but an arena where intelligences compete, where survival is contested, where threats can arrive from the dark after travelling for millions of years? It would fundamentally change our relationship with the universe. We would know, with absolute certainty, that we are not unique, that intelligence has arisen elsewhere, that the laws of physics and chemistry and biology that gave rise to us have done the same in other places, around other stars. This knowledge would be simultaneously thrilling and terrifying. We would gain a cosmic context, a sense of being part of something larger than ourselves, but we would also lose the comfortable assumption that we're safe in our isolation, that the universe, while vast and uncaring, is at least neutral rather than actively hostile. Let your mind drift now like a cloud across a twilight sky, thoughts moving slowly without urgency. The questions we're exploring are large, but you are small and safe, here in this moment, this breath, this heartbeat. December 19th approaches, marked on calendars in observatories around the world, circled in red in planning documents, the subject of telescope time proposals and observation schedules being finalised even now. That is the date when 3 Atlas will make its closest approach to Earth, still a safe 270 million kilometres away, nearly twice the distance from Earth to the Sun, far beyond any range where gravitational interactions could pose a threat, but near enough that our best telescopes will have their clearest views, their best opportunity to resolve details, to gather the data that might finally answer the questions that have been accumulating since July. Hubble will observe it, that venerable space telescope that has been humanity's primary eye on the universe for over 3 decades, the observatory that has given us images of galaxies at the edge of the observable universe, that has photographed the births of stars and the deaths of supernovae, that has measured the expansion rate of the universe and discovered dark energy. Hubble's resolution in visible light wavelengths is unmatched by any other facility. When it points at 3i Atlas in December, when it captures image after image over multiple days, we'll see the shape of the coma with unprecedented clarity, the structure of any jets or fans of material streaming, from the nucleus, the morphology of the dust cloud and how it changes over time. Webb will train its infrared eyes upon it, those gold-coated beryllium mirrors that have been observing the cosmos in wavelengths invisible to human eyes since it began science operations in 2022. Webb sees heat. It sees the glow of warm dust particles radiating in the infrared. It sees molecules that are transparent to visible light, but opaque to infrared. When Webb observes 3i Atlas, it will penetrate any dust obscuration, will reveal what's happening beneath the visible surface, will measure temperatures and composition with precision impossible for visible light telescopes. If there are temperature gradients that don't match solar heating patterns, if there are hot spots that suggest internal heat sources, if there are emission features that indicate exotic chemistry, or something beyond chemistry, Webb will find them. Dozens of ground-based observatories will coordinate their observations, from the massive 8 and 10 metre class telescopes on mountaintops in Chile and Hawaii, to smaller university facilities to amateur astronomers with backyard instruments who've proven time and again that passion and dedication can contribute meaningful data to professional research. The international coordination will be unprecedented, with observations planned around the clock, across multiple time zones, ensuring continuous coverage as 3i Atlas rotates and evolves. Spectroscopic observations will break the light into thousands of individual wavelengths, creating detailed chemical fingerprints. Photometric observations will measure brightness changes over time, looking for variations that might indicate rotation or outbursting activity. Polarimetric observations will measure how the light is oriented, providing information about the size and shape of dust particles in the coma. For several days, perhaps even weeks, this visitor from beyond will be studied with an intensity rarely focused on any single object, with resources and attention usually reserved for the most important astronomical events, for eclipses and asteroid close approaches and supernova explosions in nearby galaxies. The data will flow in terabytes, filling hard drives and taxing data pipelines. creating work for researchers that will continue for months and years after the observations themselves are complete. What will we see? This is the question that keeps astronomers checking their calendars, reviewing their observation plans, testing their software pipelines, writing the analysis code that will process all this incoming data. This is the question that interrupts sleep, that creates both excitement and apprehension, that represents the culmination of months of watching and wondering. The December observations will either confirm or refute Loeb's predictions about the gas cloud. If 3I Atlas has been losing mass through natural outgassing at the rate required to produce the observed acceleration, if momentum conservation is operating as it must, then there should be an enormous cloud of gas and dust surrounding the nucleus, easily detectable by any competent instrument, unmistakable in its extent and brightness. Momentum conservation demands it. Physics requires it. If we don't see that cloud, if the coma is modest and unremarkable, roughly what we'd expect for a comet of this size at this distance, without the extraordinary mass loss that the acceleration implies, then the acceleration cannot be explained by conventional rocket effect. Something else must be producing the thrust, something that doesn't rely on ejecting mass, something that operates through different principles. We'll also see what colour it is. The blue glow observed at perihelion was recorded by multiple instruments, but those were solar observation satellites, not designed for detailed spectroscopic analysis of comets. With dedicated observations from Hubble and Webb, we'll get precise spectral measurements, identifying exactly which molecules are present, which emission lines dominate the spectrum. If the blue colour persists, if it's still glowing in ways that don't match any known cometary processes, that will demand explanation. If it has returned to a normal red or green colour consistent with regular cometary composition, that would suggest the blue phase was temporary, driven by specific conditions at perihelion that have now passed. The trajectory data will also improve dramatically. Right now, the uncertainties in 3I Atlas's position and velocity are relatively large. It's far away, faint, difficult to pinpoint precisely. But as it approaches and brightens, as more telescopes track it more frequently, those uncertainties will shrink. We'll know with high precision whether it's following a purely gravitational path or whether there are continuing non-gravitational forces acting on it. Any further maneuvers will be detected immediately. If it begins to alter its course in ways that cannot be explained by outgassing, that would be deeply troubling, and perhaps most importantly, we'll simply see what it looks like in unprecedented detail. Hubble's resolution, while not enough to see surface features on such a distant object, should at least reveal the overall shape, the structure of the coma, any jets or unusual emission patterns. Webb's infrared capabilities will show us what's happening beneath any dust obscuration, will reveal thermal signatures, will analyze chemical compositions in wavelengths inaccessible to other instruments. These observations will generate terabytes of data that scientists will analyze for months and years to come, searching for clues, testing hypotheses, building models. There are 4 basic possible outcomes, each with different implications. First, 3I Atlas could look completely normal. The gas cloud is there, the spectral signatures match natural cometary processes, the trajectory is purely gravitational, the anomalies of perihelion were temporary quirks that natural processes can explain once we understand the specific chemistry and physics involved. In this case, the scientific mystery remains interesting but ceases to be alarming. We catalogue another unusual interstellar visitor, write papers about its unique properties, and move on. Second, some anomalies could persist but remain explainable by natural processes we don't fully understand. Maybe there's less gas than expected, but still enough to account for the acceleration if we adjust our models. Maybe the spectral signatures are unusual but consistent with exotic chemistry from an alien star system. Maybe the trajectory shows small deviations, but nothing that clearly indicates intentional maneuvering. In this case, the debate continues, with mainstream scientists arguing for natural explanations and skeptics like Loeb pointing out that the evidence is at least consistent with artificiality, even if not demanding it. Third, major anomalies could persist in ways that natural explanations struggle to accommodate. No significant gas cloud, continuing blue emissions that don't match known chemistry, trajectory deviations that look like course corrections rather than random outgassing effects. In this case, the scientific community would fracture. Most would still argue for natural explanations, insisting we simply don't understand the physics well enough yet, that declaring something artificial is premature. But a significant minority would begin to seriously entertain the possibility that 3i Atlas is designed, that we're observing technology rather than geology. The debate would intensify, more resources would be devoted to observation, and possibly missions to intercept future interstellar visitors would be prioritized. Fourth, and most dramatically, 3i Atlas could do something that is simply impossible to explain naturally. It could change course in an obvious and unmistakable way. It could emit signals. It could separate into multiple objects. It could do something that clearly indicates intelligence and purpose. In this scenario, everything changes. We would know immediately and certainly that we are observing artificial technology. The questions would shift from, is it artificial, to what is it doing, and what do we do about it? Which of these outcomes will we see? At this moment, late in the evening of your day as you rest and listen, no one knows. The observations have not yet been made, the data has not been gathered, the analysis has not been performed. We exist in a state of uncertainty, waiting for December to arrive and answer our questions. This waiting is itself interesting from a philosophical perspective. We are suspended between possibilities, between the comfortable assumption that the universe is full of natural wonders but devoid of other intelligences, and the revolutionary possibility that we've been found, that we're being watched or assessed or perhaps even judged by intellects, not our own. This liminal space, this threshold between what we think we know and what we might discover is both exciting and unsettling. Throughout human history, we have wondered whether we're alone. Ancient peoples looked at the stars and imagined gods living there, watching us, sometimes intervening in human affairs. As our understanding of the cosmos grew, the gods retreated, replaced by natural law, by physics and chemistry and evolution. The universe became comprehensible but also lonely. No gods, no angels, no aliens watching from the dark. Just us, adrift on a tiny world orbiting an average star in an unremarkable galaxy. But the question never died. As we discovered how vast the universe is, how many stars exist, how many planets orbit those stars, the statistical arguments became overwhelming. There should be other life out there. Not just primitive bacteria clinging to existence in harsh environments, but complex, intelligent, technological life. Civilizations that arose millions or billions of years before we did, that have had time to spread across their home galaxies, that might have noticed us by now, that might have sent explorers or messages or something to make contact. The fact that we haven't detected them, haven't heard signals, haven't found any evidence of their existence, is called the Fermi paradox after physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox has dozens of proposed solutions. Maybe intelligent life is incredibly rare, arising only once in a trillion star systems. Maybe it's common but always destroys itself before developing interstellar capability. Maybe it's common and long-lived but chooses not to expand, content to stay home. Maybe it's all around us, but hiding, observing quietly, following some ethical guideline not to interfere with younger civilizations. Or maybe, as the berserker hypothesis suggests, intelligent life was once common, but was systematically eliminated by self-replicating machines programmed or corrupted into genocidal purpose. Maybe the galaxy was once filled with the voices of countless civilizations, and maybe they all fell silent one by one as the probes arrived. If 3i Atlas is such a probe, if it represents that dark answer to Fermi's question, then humanity stands at a threshold not of discovery but of trial. We would learn that we are not alone, but we would learn it in the worst possible way. Not through the receipt of a friendly radio message, not through peaceful first contact with curious explorers, but through the arrival of an executioner sent by makers long dead, still carrying out programming written in an alien language millions of years ago. Even this scenario, as dark as it is, carries a strange kind of meaning. To be judged worthy of elimination would mean we matter on a cosmic scale. We would be significant enough, threatening enough, to warrant attention. Our radio signals leaking into space, our probes exploring the solar system, our slowly growing technological capability would mark us as something that needs to be addressed. We would no longer be insignificant. We would be players in a game whose rules we don't understand, whose stakes are total. But let us pull back from these speculations into something more grounded. Let us remember that the most likely explanation remains the simplest. 3i Atlas is a comet, unusual because it formed around a different star under different conditions, remarkable in its properties but natural in its origin. The anomalies will be explained. The December observations will show something that fits within our understanding of physics and chemistry, even if it expands that understanding. We will learn something new about how the universe works, will add to our catalogue of cosmic wonders, and will continue our patient search for signs of other intelligence through radio telescopes and careful analysis. This is what we should expect. This is what decades of astronomical experience teaches us to anticipate. The universe is strange, but it is not malicious. Objects behave according to natural law, not according to intent. When we find something puzzling, the answer is almost always that our models are incomplete or our data is insufficient, not that we've stumbled upon something designed by aliens. And yet we cannot entirely dismiss the possibility, however small. We cannot pretend that the questions Loeb raises are meaningless or unworthy of consideration. We cannot assume that because something seems unlikely it is therefore impossible. The universe has surprised us before. It will surprise us again. And while the surprises are usually natural phenomena that challenge our theories, could they not occasionally be something more? Could they not sometimes be intelligence, artifice, purpose? Let your breathing be your anchor now, in and out, steady and calm. Feel the rise and fall of your chest, the gentle rhythm that sustains your life. Whatever mysteries the cosmos holds, whatever visitors might pass through our system, you are here, alive, aware, capable of wonder. That itself is remarkable. As you rest, as you allow your mind to gently disengage from these large questions and drift towards sleep, consider one final thought. The exploration of these ideas, the willingness to contemplate scenarios that might be uncomfortable or frightening, is itself a kind of courage. To look at the universe honestly, to acknowledge our vulnerability as a single species on a single planet in a cosmos of incomprehensible size, to consider that we might not be alone and that any neighbours we have might not wish us well, this requires a kind of bravery. But it also connects us to something larger. For all of human history, people have looked at the night sky and wondered. They wondered what those points of light were. They wondered if other beings looked back. They wondered about our place in the grand scheme, about meaning and purpose and destiny. We are those same people, asking those same questions, but armed now with instruments and knowledge our ancestors could not imagine. We can actually detect visitors from other star systems. We can actually analyse their composition and trajectory. We can actually gather data that begins to answer questions that were pure speculation just decades ago. Whether 3I Atlas is a comet or something more, whether the December observations show the expected or the unprecedented, the very fact that we can observe it, study it, debate its nature, this represents an achievement of the human spirit. We have built the tools to explore the cosmos. We have developed the knowledge to interpret what we find. We have maintained the curiosity and courage to keep looking, keep questioning, keep seeking understanding, even when that understanding might reveal uncomfortable truths. In a few weeks, we will know more. The telescopes will observe, the data will flow, the analysis will begin. Whatever is revealed will be genuine, based on evidence rather than speculation, grounded in measurement rather than imagination. Until then, we wait in that suspended state between possibilities, between the known and the unknown. And in that waiting, there is a strange kind of peace. Not the peace of certainty, but the peace of acceptance. We do not control the universe. We cannot determine whether 3I Atlas is natural or artificial, benign or hostile, interesting or world-changing. We can only observe, analyse, respond to what we find with the best of our capability and wisdom. There is a humility in this, a recognition of our limitations, but also a dignity in the effort itself. You are part of this story simply by being human, by being alive at this moment in cosmic history when such questions can be asked and observations made that might answer them. Your existence matters in the great pattern, not because you will individually influence what happens with 3I Atlas, but because you are part of the species asking the questions, seeking the answers, confronting the mysteries with curiosity rather than cowering in ignorance. As sleep approaches, as your consciousness begins to dim and drift, let these thoughts settle like snowflakes, gentle and cool. The cosmos is vast and we are small. The questions are large and we are finite. But in the asking itself, in the wondering and exploring and seeking to understand, we achieve something meaningful. We reach beyond ourselves. We touch the infinite, if only for a moment. The December sky will soon hold answers. Whatever they are, we will face them together, as we have faced every challenge and mystery throughout our long history as a species. We are the children of stardust, born from supernova remnants, shaped by billions of years of cosmic evolution. We have survived ice ages and asteroid impacts, plagues and wars, disasters natural and self-inflicted. We've endured. We have persisted. We have looked up at the stars and refused to accept ignorance as our fate. If 3I Atlas is merely a comet, we will marvel at its strangeness and add it to our understanding of how diverse the universe can be. If it is something more, if it represents that first hard evidence that we are not alone, we will rise to meet that knowledge with whatever wisdom and strength we possess. We will communicate, or we will defend, or we will adapt, or we will do whatever the situation demands. That is what we do. That is what we have always done. That is what we will continue to do for as long as our species endures. And in this moment, right now, as you rest in warmth and safety, none of those cosmic questions change the simple fact of your existence. You are here. You are breathing. You are alive in this universe of wonders and mysteries. The visitor from beyond may be natural or artificial, friendly or hostile, significant or mundane. But you are significant simply by being. Your life has value independent of cosmic context. Your experience of this moment, this quiet breathing, this gentle descent into sleep, this is real and important and sufficient. Let the questions go now. Release the need to know, the urge to solve, the pull to understand everything. Some mysteries will be answered in time. Others may remain forever beyond our grasp. Both outcomes are acceptable. Both are part of the grand pattern of existence. Your eyes are heavy, your body is relaxed, your mind is quiet. The universe continues its slow dance, stars burning, planets orbiting, comets or probes or whatever they are crossing the vast distances between suns. All of it unfolds according to its nature, whether that nature is random chance or deliberate design, and through it all, life persists wherever it can, consciousness emerges wherever conditions allow, and meaning arises from the beautiful complexity of systems capable of experiencing themselves. You are that consciousness, you are that meaning, you are matter become aware, stardust contemplating stars, the universe examining itself through your eyes and thoughts. In this recognition, there's profound peace. You belong here, you are part of this. Whatever comes, whatever the future holds, whatever December's observations reveal, you have a place in the grand story. Sleep now, gently, easily. Let your thoughts dissolve like mist in morning sun. The visitor passes through our system, following its trajectory whether guided or natural, and you rest here in safety while above the atmosphere telescopes watch and wait. The universe is large and you are small, but in that smallness is perfection. You're exactly what you need to be, here and now, in this moment of quiet rest. The stars wheel slowly overhead in their ancient patterns. The sun rises and sets, marking time that has meaning only to those who count it. 3i Atlas continues its journey, approaching its closest point to Earth, carrying with it questions we may soon answer or may never fully resolve. And you continue to, breathing in and breathing out, living each moment as it comes, connected to everything through the simple fact of existence. If you've enjoyed this journey through the cosmos, this exploration of possibilities both wondrous and unsettling, please share your thoughts in the comments. Tell us where you are, what time you're listening, whether you think we're alone or watched, whether the universe is neutral or filled with intention. Subscribe if you'd like to continue these explorations together. Like this video if it brought you something of value, whether knowledge or wonder or simply a peaceful way to transition into sleep. Thank you for travelling with me tonight, for contemplating these large questions in the quiet space before dreams. Thank you for your curiosity and courage, for being willing to look at the universe honestly, even when it might look back. Sleep well, dream deeply, and rest in the knowledge that tomorrow will bring what it brings, and we will face it as we always have, together as a species, bound by our common humanity and our shared wonder at the strange and beautiful cosmos we call home. Good night, traveller. The stars await your dreams. Thank you for your curiosity and courage, for being willing to look at the universe honestly, even when it might look back. Sleep well, dream deeply, and rest in the knowledge that tomorrow will bring what it brings, and we will face it as we always have, together as a species, bound by our common humanity and our shared wonder at the strange and beautiful cosmos we call home. Good night, traveller. The stars await your dreams.